Hi. So let's briefly look at the concepts involved in this assignment, and then we'll start with solving the actual problems. Let's first review forward checking with this example of the standard coloring problem where no two adjacent nodes, for example A and B, can take the same color. So what we have done is we have already assigned the color blue to A and adjusted the domains of all the variables accordingly. Now let's look at the variable B and assign the color green to it. So I'm crossing off red here just to indicate that. So now we have assigned the color green to the node B. So let's look at what forward checking does. What forward checking does is that it looks at the variable which was just assigned, which is B in this case, and then looks at all the other unassigned variables, which are C, D, and E. And from the domains of the unassigned variables, it removes those values which are inconsistent with the variable that we just assigned, that is B. So let's look at the node C first. So C can either be green or red. Now, since the node B has color green, the node C cannot have the color green. So we cross off that value. Similarly, the node D can also not have the color green. So we cross off this value. However, node E does not have any direct constraint with the variable B. So an assignment to variable B does not cross out any values of the node E. So what forward checking basically did was it looked at the unassigned neighbors of B, which were C and D, and removed the values which were inconsistent with the assignment that we just gave to B. So now let's look at what arc consistency does. So what arc consistency means is that if you have two variables, x and y, and you're considering the arc which is directed from x to y, that is x is the tail, it looks at all the values in the domain of x, and let's say the domain is x1, x2, and so on. And for each value, so let's say x1, it checks if there is any possible value in the domain of y. So suppose y had the domain y1, y2. So it looks at x1, sees if either of y1 or y2 are compatible with x1. If they are, then it keeps x1. Then we look at x2, and then it again checks if any of y1 or y2 are consistent with x2. Let's suppose that neither y1 nor y2 are consistent with x2. So what arc consistency would do, it would remove the value x2 from the domain of x. So it basically just removed the values from the domain of the tail node that did not have any corresponding possible value in the head node. And when we think of this graph, the arcs between A and B are sort of undirected. So we have to consider both directions, so A to B and B to A, and similarly C to D and D to C. So we'll be considering all these arcs, and arc consistency makes all of these arcs consistent. So let's take the example that we did previously. That is, suppose we just assigned the value green to the node B. So crossing out red again. And let's see what arc consistency would do. So let's first look at the arc E to C. So you could look at arcs in any arbitrary order. I'm just taking this so that we see some interesting point later. So the variables in the domain of E are blue, green, and red. And in the domain of C are green and red. Now blue is compatible with both of them, so blue stays. Green is compatible with red, so green stays. Red is compatible with green, so red also stays. So this arc does not delete any value from C. Now let's look at the arc D to B. Now the value blue is consistent with green, so it stays. The value green is not consistent with green, so we have to cross it out. The value red is consistent with green, so it stays. Okay. Now let's look at C to B. So again, the value green is not consistent with any value in domain of B, so we cross out green. The value red is consistent, so red stays. Now notice that we had already checked the consistency of this arc, but the value of C just changed, so we'll have to re-examine this arc. So we again examine E to C. Now in E, the value blue is consistent with red, the value green is consistent with red, the value red is not consistent with any value here. So we cross out this. So what arc consistency did was it looked at all arcs between all variables in both directions and enforced consistency for all of them. And we saw that a change in B made C change, and that eventually made E change. So the change propagated because we are enforcing consistency for all arcs. So you can see that this did more work than forward checking, which had not removed this value. In the first question that we have, what we are asked is that if we run forward checking / arc consistency after variable assignments to various variables, what values might change? So the first part asks that we just assigned a value to the variable A, and the question is which other variables might have their domains changed. So as we saw, that forward checking can only affect those variables which are direct neighbors of this. So the only variables whose domain might change are C, B, and D. So C, B, and D. For the next part, what we are doing is we assigned a value to A, ran forward checking, and then assigned a value to B, and then ran forward checking again. Now, again, only the neighbors of B can get affected, but notice that since we already ran forward checking after assigning a value to A, the value of B that we choose has to be consistent with the selected value for A. So even after we select B and run forward checking, the chosen value of A does not get affected. So the only two variables that can get affected are C and E. So even though B has 3 neighbors, A was already assigned and consistent with B. So the only other 2 variables that can change are C and E. Now the next part asks us to run arc consistency after assigning a value to A. Now when we assign a value to A and enforce consistency for the arc C to A, the value of C might change. Similarly, D to A might change the value of D. Similarly, the value of B can change. Now, since the value of B changed, we have to examine the arc E to B, and the value of E might change then. Similarly, the value of F might change. So basically, the neighbors of A can change and can also propagate the change. So all the variables except A could change in this case. So the answer here is B, C, D, E, and F, all of them except A. For the last part, what we are doing is assigning a value to A, enforcing consistency of arcs, then assigning a value to B, and then again running arc consistency. So in the second round where we run arc consistency, the value of E can change because we just assigned B. The value of C can change again because we just assigned B. Since the value of C changed, the value of F can also change. The trick in this part is that after we assign B and run arc consistency, the value of A will not change because the possible values of B were already consistent with this value of A. Now, since the value of A did not change, D cannot change. So, when we chose a value for B, ran arc consistency, A did not change and therefore D finally did not change. So the only 3 variables that could change when running arc consistency after assigning B are C, E, and F. Before we start question 2, let's review an important concept about arc consistency for trees. Let's first look at the algorithm that we saw in class, which gave us a solution for tree structured graph by just applying arc consistency. What that algorithm did was it applied arc consistency from right to left. So the first arc that we would consider is C to E, and we would remove those values from C's domain which do not have any possible assignment in E. So suppose the values in E were E1, E2, the values in C were C1, C2, C3. Suppose C3 did not match up with any of these 2 values, so we would cross C3 here. Similarly, we made this arc consistent, removed the values from the domain of B that have no consistent D. Then we removed the values from the domain of B which have no consistent C, that is, are not consistent with either C1 or C2. Then finally, we removed those values from the domain of A which do not have any consistent value of B. So once we are done making all these arcs consistent, we could now start assigning values to each of these variables. So suppose finally there were just two values that were left in the domain of A, say A1, A2. What we were guaranteed were that if we chose any of these values, say we chose A1, since the arc A to B is consistent, we can find some possible value of B that is consistent with A1. Let's say that value was maybe B2. Now, since this arc was consistent and B2 did not get removed, B2 has some possible assignment of C that is consistent with B2. So maybe that assignment is C1. So we can choose that value of C. And similarly, there is some possible value of D that we can choose if we chose B equal to B2. And similarly, after choosing C equal to C1, we can choose some possible value of E which was consistent with C1. Note that we could do this because we had made all these arcs consistent and we were assigning values in the correct order. For instance, when we assigned a value to B, that value was already consistent with the value that we had assigned to A, and we knew that the arcs that remained were consistent, so we could always find a value for the other variables that would sit well with B2. So it was kind of this ordering which was left to right assignment which made this possible. And note that we never had to backtrack. So once we enforced arc consistency, we chose some value of A, we could then find some value of B, then we could find some value of C, then D, and then E. We never had to backtrack on any variable. Whatever value we chose, we were guaranteed that there is a successful assignment that is consistent with that value. So the moral of the story is that if we enforced arc consistency on a tree just once, and then we assigned values in this left to right order, we are guaranteed that we'll never backtrack. Now, I've just drawn another graph below the original graph which does not have directions on any of these edges. Even if we enforced arc consistency on this graph, so suppose we enforced arc consistency on this graph. So the arc A to B, B to D, C to E, and B to C are all consistent. I mean, this graph is undirected, therefore there are 8 arcs. And here we needed consistency for only 4 arcs to guarantee that an assignment in the left to right order works. So here having arc consistency on more arcs still does not break this guarantee. So the point of showing this graph to you was just to say that even if the arcs do not have any particular direction, enforcing arc consistency on this undirected graph still gives you the same guarantees as the above graph where we had assigned directions to edges. So if we have this tree and we make this tree arc consistent, the guarantees still hold that if we assign values in a left to right order, we'll never have to backtrack. However, if the graph that we are considering is not a tree, for instance, if I could say at this edge between A and C, now this is no longer a tree, and even if we enforce arc consistency, we are not guaranteed that the remaining values and some possible assignment ordering will give us a solution. So if in the case of a general graph, even if we enforce arc consistency, we can not say anything about being guaranteed to find a solution. What we can say, however, is that if we assign some value to A in this case, then the remaining graph is still a tree. So if we assigned a value to A, then ran arc consistency, then we would immediately know whether or not that value that we assigned to A was good or not. For instance, suppose we assigned value A equal to A1, and A1 was not part of any solution. As soon as we assign A equal to A1 and run arc consistency, the remaining graph is a tree. So we'll realize that A1 was not a good value. Then maybe we'll assign A2, and suppose A2 was a value which can give us a possible solution. Then the remaining graph is a tree, and then we can use the algorithms that we have seen above to infer the solution for the remaining variables. So we had to possibly go over all values of A, but as soon as we got to a correct value, running arc consistency told us that a solution exists to the remaining variables. So for instance, in this case that I showed, where we drew an extra arc between A and C, we might have had to backtrack at most d minus 1 times and eliminate all the wrong values of A. As soon as we got to the right value of A and ran arc consistency, we would have known that that value of A is good, and then we would have just done tree structure inference. So in this case, we just had to backtrack d minus 1 times. In this question, we are not enforcing arc consistency at every step. What we are doing is we are enforcing arc consistency at even steps. So we'll first assign one variable, then the second variable, and then run arc consistency. Also, we are initially enforcing arc consistency. So in this case, for instance, we are first enforcing arc consistency, then assigning A, then assigning B, then enforcing arc consistency, then assigning C, then D, then enforcing arc consistency, and then finally assigning E. And similarly for these cases. Now, in this case, notice that we initially assigned arc consistency. And what we had previously seen was that if we initially make all the arcs consistent, then a left to right ordering of assignment of variables is guaranteed to have no backtracking. And notice that this assignment is from left to right. So we are guaranteed that we'll never have to backtrack just because we initially made all these arcs consistent. So basically, even if we were not having arc consistency after assigning B or after assigning D, we would still never have had to backtrack just because we initially enforced arc consistency. So the answer to this part is 0. Let's first consider the third part. What I've done below is just redrawn the graph where I put C first, then B, A at the last. The edges are basically the same. I've just reordered the nodes and redrawn the graph. Now, since we initially enforced arc consistency, when we pick a value for C, say C1, we are guaranteed that there is a value of B which is consistent with that value of C, since this arc was consistent. So we can always find a B that is consistent with C1. Therefore, we can always find an A which is consistent with that value of B. Similarly, we can find a D which is consistent with that value of C, and we can find an E which is consistent with that value of D. Therefore, what I've shown is that you'll never have to backtrack. This is just a linear ordering written with C as the root node instead of A as the root node in this case. So again, we initially enforced arc consistency and then basically assigned values in a linear order with C as the root node in this case. But the proof is basically the same as what we had seen earlier, in the sense that if you assign values from left to right with some root node after enforcing arc consistency, then you will never have to backtrack. So again, even in this case, the answer is that you never backtrack, therefore 0. Now, the second case is a slightly tricky case because here the ordering does not really correspond to any linear ordering with any root node. Instead, so what we are doing here is first assigning A. So first we are enforcing arc consistency, then we are assigning A, then we are assigning E, then B, then D, then arc consistency, and then finally C. So the problem here is that when you pick a value for A, say A1, and you pick a value for E, say E2, since after picking A1 you could not enforce arc consistency, you are not guaranteed that the value of E that you chose, which was E2, will give you a valid assignment for B, C, and D. So basically, the pair A1, E2 is not guaranteed to give you a solution for the remaining tree just because you could not enforce arc consistency after assigning A. If you had enforced arc consistency after assigning A, then since this is just a tree structured CSP, the values of E which did not give any possible solution would have been removed from here. So if E2 were a bad value, it would have gotten removed after we applied arc consistency after choosing A. But since we did not do that, the bad values of E are possibly still around and we might choose them. So maybe we chose E2, which does not give any possible solution for B, C and D. A simple case would be that, say your constraints are A not equal to B, and similarly B not equal to C, and here as well, and here as well. And suppose all of these variables were between 0 and 1, and suppose you chose A1 equal to 0, and then when you were exploring E, maybe you chose this equal to 1. Now this will not give you any possible solution, but E2 equal to 1 did not get removed since you did not apply arc consistency after choosing it. So you might make a bad choice at E, but now you are allowed to run arc consistency after you have chosen E. As soon as you run arc consistency, since the remaining 3 nodes still form a tree structure, you'll realize that E2 is a bad choice. So you chose some value for A, which was guaranteed to have a solution since it's a tree structured CSP and you had initially run arc consistency. So A1 was a good value, but E2 was a bad value with respect to A1. Then as soon as you choose A2 and then run arc consistency, you realize E2 is a bad value. So in the worst case, you might have chosen D minus 1 bad values for the node E. But as soon as you got a good value, you ran arc consistency, you knew that it's a good value and you will never have to backtrack from E again. Now you are just left with these 3 nodes, B, C and D, and the order in which you are assigning them is B, D and then C. So again, the same problem might occur. Since after assigning B, you do not enforce arc consistency, assign the value that you choose for B, say B3, and then the value that you pick for D, say D2. So B3 and D2 might be inconsistent with each other. And since you only realize that after assigning D2, you might choose at most again D minus 1 bad values for D. So the total number of times that you backtrack is D minus 1 plus D minus 1. The reason that it's plus and not into is that as soon as you got a good value for E, as soon as you got a bad value for E, you never went down that path again. So because as soon as you got a bad value for E, you ran arc consistency then and there, and you realize that it's a failing value and you never explored the other nodes recursively. So you could have failed at most D minus 1 times at E, but discovered your failure just then, and then you might have failed at most D minus 1 times at this node. So the answer to this part is 2D minus 2. Now the graph shown here is not really a tree structured graph, but notice that as soon as you assign the node A, it becomes a tree structured graph because it basically separates out into 2 subgraphs, BDF and CEG, both of which are tree structured graphs, and there we could apply the concepts that we saw earlier. So in this case, you're applying arc consistency again here at the first node, before exploring the first node, then after exploring B, then after exploring D, after exploring F, and so on. Now, the initial arc consistency is not guaranteed to give you anything because the current graph is not a tree structured graph. So this initial enforcement of arc consistency will not necessarily tell you anything or give you any guarantees. Now, then you assign a value for A, which may or may not be a good value. So for instance, there could be A1, A2, and so on, AD, so D values of A that remain after the first time you run arc consistency. But since that was not a tree structured graph, the first arc consistency does not guarantee you that the remaining values will actually lead to a solution. So maybe after that you chose A1, and maybe A1 is a bad value. So you won't realize it just now because you're not allowed to run arc consistency after choosing a value for A. You'll pick a value for B and then you'll realize that this value for A was not a good value. So you'll maybe explore all possible values of, so what you'll actually realize is that the pair A1, B1 is not a good pair. So basically in the worst case, you'll have to iterate over all pairs of AB until you finally find a pair which is feasible. So only after you have chosen one value for A and one value for B are you allowed to run arc consistency. So in the worst case, you'll have to explore all the possible pairs and you'll have to backtrack for all of them except for the correct one. So the number of pairs are d square and you'll have to backtrack d square minus 1 times till you come to this particular point and are successful in a valid assignment for A and B. So we have d square minus 1 backtrackings till this point. Now notice that after you have assigned a value for A and B, you are assigning D first and then F, which is a valid linear ordering. And in the lower subgraph, you're assigning C first, then E, then G, which is also a valid linear ordering. So after you have enforced arc consistency at this point, on your two trees that remain in the graph, you are assigning variables in a linear order, so you'll never have to backtrack there. Therefore, you only backtrack d square minus 1 times. So let's first consider the third case. The third case is kind of similar to the first case. Here we are first exploring A, then exploring B, and then applying arc consistency. Here we first explore C, then A, and then apply arc consistency. But basically we are still going to search over all pairs of AB, and here we'll still search over all pairs of AC until we find a pair which is a valid pair for the remaining variables. So we'll iterate over all values of C. For each of those values, we'll look at all values of A. Whenever we assign A, we'll run arc consistency and realize whether or not that pair is valid. So again, in the worst case, we might have had to look over d square minus 1 pairs. And after we have assigned the variables C and A, we are assigning the variables in the remaining part of the graph, for instance E and G, linearly. Similarly, we are assigning first F, then D, then B, which is also a linear order on the remaining 3 nodes here with F as the root node. So basically, after we assign AC, we are left with the graphs F, D, and B. And we are assigning these nodes linearly. Similarly, we are assigning G and E linearly. So we'll never have to backtrack after we find a valid CA pair. And we'll find those after at most d square minus 1 backtrackings. So again, the answer to this part, like the first one, is d square minus 1. Let's now consider the second part. What we are doing here is first assigning F, D, then B, then A, and then CGE. So notice that while the first 3 variables, or like until A is assigned, the remaining graph is not really a tree. So even when we have assigned F and D and then we enforce arc consistency, the remaining part of the graph still has this cycle. So we still don't know if we are going down the right path, and we have no guarantees whether the current solution is a feasible solution. Only after we have assigned A can we detect whether or not the assignment of these 4 variables was valid. So basically, until we have assigned A, we cannot say anything about the part of the search tree or the values that you have assigned to F and D and B. So essentially, for all these 4 variables, there are d to power 4 possible combinations. And in the worst case, we'll have to go over all of them, and maybe the last one that we find would be valid. So as soon as we have selected a combination, we get to run arc consistency on A, and the remaining graph is tree structured. So as soon as we have a combination of all these 4 variables, we know whether or not that combination is good. But it is only, so basically we'll have to explore all possible combinations of these variables until we find one that is valid and has a feasible solution for the other three variables. So in the worst case, we'll go over all combinations and the last one that we discover will be valid. So we might have to backtrack d to power 4 minus 1 times to find a good combination of these four variables. Now, after we have found that combination, the only variables that remain are the three shown below, C, E, and G. Now, notice that there's a trick here, which is that we are not assigning these nodes in a linear order. We are first assigning C, then G, then E. So issues that we saw in the previous part, which were occurring, for instance, between A and E, might occur here. So maybe after you assign the value to C and then you assign a value to G, only then you'll be able to run arc consistency, and then you'll realize that the pair that you chose for C comma G is not valid. So you might have to do D minus 1 additional backtrackings because you are not exploring these nodes in a linear way. So for at G, you might have to do D minus 1 additional backtrackings. So the answer to this part would be D to power 4 minus 1. These many backtrackings to get a valid combination of these four nodes. And then plus D minus 1. The D minus 1 part comes because we are first expanding C, then G, then E. And the values of C that remain after arc consistency are all valid. But when we choose some particular value here and then choose some particular value here, then maybe that value of G is not consistent with the value of C that we just chose. So we might be doing D minus 1 additional backtracks at this node in this case. And the answer for this is D to power 4 minus 1 plus D minus 1. So before moving on to question 3, let's review MRV and LCV. The full forms are MRV refers to most restricted variable, and the MRV criteria tells us which node to explore next. So suppose in this case we have already explored or assigned a value to B and A, which is blue and green, and the MRV criterion would tell us which variable should we explore next. So it looks at all the variables and chooses the one which has the least number of values remaining in its domain. C has 2 values, D has 3 values, E has 4 values. So the MRV criteria will choose C. So here, if we use the MRV criteria to explore the next variable, it will choose the variable C because it has the most restricted domain. The LCV criteria is least constrained value, and it tells us which value to choose next. So when we are exploring a particular variable, we can possibly, so for instance, if we were exploring C, we could choose red or yellow to explore the next, to go down the search tree. So LCV tells us which value should we explore next. The logic behind LCV is that if you choose the least constrained value, you might maximize your chances of success in that part of the search tree and find the solution early. So maybe let's look at the variable E for this case. So E has 4 values, blue, green, red, and yellow. Among these values, the least constraining value is green, because if you choose the value green here, you do not add any additional constraints to C or D, because C or D anyways cannot be green since blue is already green. If you chose any other value, for instance, if you chose blue, you'll add some constraint. So you'll add a constraint to D. If you chose red or yellow, you'll add one constraint to both C and D. So therefore, exploring green adds the minimum number of constraints to the other variables. Therefore, the least constrained value is green. Let's consider the third question. What the question asks you to do is consider a modification of the backtracking algorithm where you're finding every possible assignment instead of just one possible satisfying assignment. So we backtrack whenever the solution is found. So even if we find a solution in the normal backtracking search we return, here we backtrack again until we have found all the solutions. And what the question asks is for various graphs, whether MRV will have an effect on the number of nodes expanded and whether LCV will have an effect on the number of nodes expanded. So the first case is slightly straightforward because no nodes are connected to each other. Therefore, neither of these constraints will have any effect because for each of the variables you will be just going down all possible values independently. Therefore, neither MRV nor LCV will have an effect. Therefore, this option. For this case, let's consider the least constraining value first. In fact, let's consider the least constraining value for a slightly more general case that we saw as an example earlier. In this case, suppose we are exploring this partial search tree where we have assigned A, we have assigned B, and suppose now we are exploring the node E. And the least constraining value tells us to explore the value green. So we put this value green and then find all possible solutions given this is blue, this is green, and E is green. And maybe we'll find a few solutions. But we are not done yet. We still will have to explore the other possible values. We'll still have to explore what if we put E equal to red. So after green, we will still have to explore red. We just explored green first, but we still have to explore red because A equal to blue, B equal to green, E equal to red, C equal to then maybe yellow and blue, and D equal to maybe red is also, or something, D equal to maybe blue is a feasible solution. So even if we explored green first, we still have to explore red later. And we still have to explore the other two values as well, which are blue and yellow. So what LCV did was just told us the ordering in which we are exploring this, but we eventually had to go through all of them to find all possible solutions. Therefore, in this case, the LCV heuristic does not affect the total number of nodes. It just affected what order in which we are exploring the values, but since we anyways had to explore all values, even if we went down the green path, had a success here, we still had to come back because we want all possible values, and then maybe we had to go down the red path and then the blue path. So even if we found a success here, we had to come back and explore the other values. Therefore, LCV does not have an effect here. By a similar logic, LCV will not have an effect for any of the cases that have been mentioned because we have to find every possible satisfying assignment. So this was kind of a trick question in that way, that LCV does not have any effect because of this modification to the algorithm. Now, MRV can typically have an effect. For instance, consider a very simple case where, say, A can be either 3, 4, 5, C can also be 3, 4, 5. Everything else can be from 1 to 5. So maybe 1 to 5. And similarly, E can be 1 to 5. And suppose the constraints are that A is equal to B and B is not equal to C, and maybe we have some other constraints. Suppose we explored C first and chose the value 5. Then maybe we explored A and again chose the value 5. So now B has no possible satisfying value, whereas D and E have some possible values left. So if we use the MRV heuristic, we would first explore B, realize that A equal to 5 and C equal to 5 is an immediate failure. We'll not have to explore these nodes for that case. So MRV saves us some computation in this case. Similarly, MRV will also save us some computation in all of these cases. Therefore, the answer to these is only MRV can have an effect. So this one, so irrespective of the structure of graph, MRV can have an effect if the nodes are connected. And since we modified the algorithm to return all possible solutions, LCV will not have an effect in any of these cases. The only case where MRV does not have an effect is where there are no constraints, where MRV cannot play any role.